Thank you again for allowing me to speak to you all today. My name is Rob Rogers. I work at the NOAA Hurricane Research Division, which is in Miami, Florida. And what I'm going to talk about today are ways that we can use observations, in particular aircraft observations, to improve our understanding and prediction of tropical cyclones. So this picture you see here is an actual picture within a Category 5 hurricane eye from one of the aircraft that we fly on. So I want to talk to you a little bit today about how we can use that data to make better forecasts ultimately. Let me see if I can advance. Is there a lag here? There we go. So the real challenge or one of the big challenges, at least with tropical cyclone forecasting, is the intensity forecasts. So if you go back and you look at the National Hurricane Center's forecast errors at the 48-hour lead time, back to 1994, so about 25 years ago or so, and you set that value to a value of 100, and then you look at how the track forecast error at least has improved over the past 25 years or so, you can see that our track forecast errors have been reduced by about 70%. However, if you look at the intensity forecast errors, that's the red line, you can see intensity forecast errors have reduced by only about 30%. So about half of the, or less than half actually, of the error reduction that we see for track forecasts. So, obviously there's an issue in terms of our intensity forecasts. They really have lagged our track forecast improvements. So one question becomes, how can our observations that we collect through the work that we do at HRD, how can those observations be used to make better TC intensity forecasts? So we have put together an experiment that's actually been on the books for about 15 years now. It's called the intensity forecasting experiment. And so there's actually been a couple papers that have come out in the Bulletin of the American Meteorological Society, one in 2006 and another one in 2013. And then there's another one that we're actually in the process of just about finishing up and submitting, and hopefully we'll get that published in 2021. But IFEX is intended to improve our prediction of tropical cyclone intensity change by addressing three primary goals. The first goal can be considered as directly trying to improve forecasts. And in terms of the observational side of that, that involves collecting observations that span the tropical cyclone life cycle across scales. So, intensity change processes span scales from the environmental scale, thousands of kilometers, down to vortex scale, maybe 100 kilometers, convective scale, 1 kilometer, let's say, and then turbulence scale and even microphysical scale. So to the extent that we can capture these with observations, we want to collect them across the life cycle, and that will go toward better model initialization as well as model evaluation. The next primary goal is what I'd call nowcasts. So that involves developing and refining measurement technologies that can provide an improved real-time monitoring of tropical cyclone intensity, structure, and its environment. And finally, the last goal I would call research or processes, really trying to get more of the fundamental physical processes and improving our understanding of those processes. In particular, those processes that we think are important in intensity change. And not just for hurricanes, not at the mature stage of a tropical cyclone's life cycle, but in particular earlier in their life cycle, whether it's a tropical storm or tropical depression or even a pre-depression. So these three goals, forecasts, nowcasts, and processes, really form the core of what IFEX does. They really provide a linkage between the observations and the modeling, the data assimilation, and the theory that form the foundation of the work that we do at HRD and within NOAA as a whole, and also within really the broader tropical cyclone community, I'd say. So what are some of the primary observational technologies that we have as part of IFEX? Well, the main platforms are, they're airborne platforms that we focus on. And so the aircraft that we use are, you see the two pictures on the left here. So we have two NOAA P3 aircraft. So those are the aircraft that punch right through the eye wall of a hurricane. That picture that I showed you at the beginning was taken from a P3. So we have two of those, and then we also have a high altitude jet called the NOAA G4. So that flies at about 41 to 43,000 feet. So about 12 to 14 kilometers or so altitude. And that primarily samples in the environment around the storm, around the tropical cyclone, but it has from time to time actually been known to overfly the inner core of the tropical cyclone. NOAA is actually also in the process of acquiring a new high altitude jet, a G550, which will have actually an even higher altitude, higher ceiling, and a longer duration and range. So we hope to get that online in the next few years or so. In terms of the actual measurements, well, we have the in situ measurements that we have from the aircraft, in particular the P3s. That includes, of course, the winds and the pressure and the temperature and moisture measurements. We also have expendables that we release from the aircraft, so they're drop-ons. These are instruments that actually fall to the ground with the parachute, and as they're falling, they measure temperature, pressure, winds, and moisture, and report that back to the plane, which we report back to the ground. We also have buoys and other types of expendables that measure ocean conditions, sea surface temperature, as well as subsurface temperature, currents, and salinity, and so forth. We also have remote sensors on the aircraft. So we have a tail Doppler radar. So you can see these antennae on the backs of the P3s, at least, the little cones that jut out from the back. Those are antennas that actually allow us to get measures of not just the reflectivity, but also the three-dimensional velocity. We also have instruments that measure the surface wind speed, the SFMR and HIRAD. And so these are basically instruments that measure the brightness of the ocean, and from that we can infer what the wind speeds are at the surface right underneath the aircraft. We have instruments that measure the wave field, the WSRA, so that tells us, what the waves look like under the aircraft, which is very important, of course, for shipping interests. Scatterometers and profilers, which will allow us to get integrated measurements underneath the aircraft, as well as estimates of the surface wind and direction. And then finally, UAS, or unmanned aerial systems. And so these pictures in the middle, you see a NASA Global Hawk, and you see what's called a Coyote UAS. These are examples of some of the unmanned systems that we either have or we partner with NASA on. And then the G4 tail Doppler radar you see in the middle there, that's a TDR that we actually put on the G4 aircraft. So now we've got Doppler radars on both P3s as well as the G4. Some of the newer instrumentation I won't have time to get into today include the Doppler wind LiDAR in the bottom right corner. So those are just ways that we can get measures of winds, wind direction and speed in areas where the tail Doppler radar cannot measure. In the absence of scatterers, basically, that the LiDAR can give us some of those measurements. So it's a nice complement to fill in those gaps. So Mikhail did a really nice job at giving an overview of the value chain, and I just kind of wanted to talk about where I think IFEX fits into this warning value chain. So I put up here a picture. I think this is a slightly older image of the value chain from a paper that Brian Golding published last year. But in particular, I want to talk about where tropical cyclones I think would fit into this value chain. So here are the peaks that Mikhail talked about. These are, I guess, what Brian calls the peaks of expertise, and then the valleys of death, so to speak, and then the bridges of communication across these various valleys. And so in terms of the tropical cyclones, the primary observations that we have that we use as part of the value chain include, of course, satellites, as well as surface observations, and then aircraft data. And then the main parameters that we try to better predict with the numerical models in terms of tropical cyclones include the minimum pressure, as well as the position of the storm and the peak winds. And so IFEX, of course, really falls on the left side of this value chain. In particular, IFEX provides the aircraft observations to improve our model forecasts of key TC parameters such as pressure and winds and position. So now I'm going to give some examples of how we're working toward addressing each of these IFEX goals. So the first goal I'll talk about are ways that we're improving the forecasts. So, one of the key observations that we use in our assimilation within numerical models are dropsons. And so there's been a problem though when you release dropsons in a high wind environment like a tropical cyclone. They often will, they'll of course drift with the wind. And so if you release a dropson, for example, near the eye wall, it can go a significant distance around the storm as it's falling toward the surface. And so this image on the left is showing an actual location where we released a dropson from a P3 aircraft, and then where that dropson moved after we released it. However, if you look at where in an older formulation, the global or the numerical models assumed a specific single location of where that drop was occurring, when in reality, of course, the drop was really moving a significant distance in the horizontal. That can have significant implications in terms of the assimilation of winds, for example, and can really give you an erroneous initialization. In the case that I'm showing you here, the dropson drifted by 15 kilometers, but there are easily cases where drops can drift completely around a storm, or halfway around the storm if it's in a particularly strong eye wall. So we actually implemented, and working with the Environmental Modeling Center within NOAA, we implemented a technique where we accounted for the drift of the dropsondes, and then we ran a series of evaluations and verifications to see how that improved the forecast. And in fact, we did see that when you account for the dropsonde drift, that's the red line here on the right panel, you can see a reduction in the intensity forecast errors just by accounting for those drifts. Another example of how we use the observations to improve our forecasts is in model evaluation. So one of the key processes that really plays a role in determining a tropical cyclone intensity is the boundary layer. Of course, the boundary layer, modulates or governs the fluxes of moisture and temperature, as well as momentum with exchanges with the sea surface. And so the left panel is showing you observations from thousands of dropsondes released in many different tropical cyclones, composited in a composite framework. So the x-axis is showing you a normalized radius, basically normalized by the radius of maximum wind. So value of 1 means right at the RMW, or radius of maximum wind. And so this is going out to 3 times the RMW. So using a composite of these dropsonde observations, we get a sense as to how strong a typical inflow is. This is radial flow, so showing flow toward or away from the center of the tropical cyclone. So in the lowest 500 meters to 1 kilometer, the boundary layer is of course governed or dominated by inflow, and you can see the strongest inflow is really concentrated at about 100 meters or so. But you do have inflow that extends over about a depth of about 500 meters to over 1 kilometer. So compare that now with a formulation of inflow with a sort of our state-of-the-art numerical model at the time, HWRF, operational numerical model at least. There's a formulation of eddy diffusivity, or mixing in the vertical, that the model used, and it was basically based on an old formulation from the GFS, I believe it was, and it essentially had mixing that was much too strong. And so when you use this value of eddy diffusivity that was much too strong, and you looked at what that composite type of inflow structure looked like, you can see the inflow layer is depicted by this black solid line was quite a bit deeper, and the magnitude of the inflow was quite a bit weaker than what we get from the observations. So that pointed to a clear bias in the structure of the boundary layer when you use this incorrect version of the eddy diffusivity, or the mixing. Now, using aircraft observations, flight level observations, we were able to get a better estimate of what the actual mixing should be. And when we corrected for that mixing and then ran it again in that HWRF model, we can see a much more consistent inflow depth as well as inflow strength when compared to the observations. So clearly a much better structure in terms of the inflow in the boundary layer when we use those corrected eddy diffusivities. What impact does that have on the actual forecast? So we ran a set of cases where we used this corrected KM, or corrected eddy diffusivity, for 2 specific tropical cyclones that underwent rapid intensification. So the top 2 lines, the solid lines, are showing you the overall error, and then the dashed lines, the red and black, are showing you the biases for both the corrected KM values in red and the incorrect in black. And so you can see that when you use the corrected KM, the intensity errors are reduced out, across all lead times, basically out to 4 to 5 days, and the biases are also reduced. So at least for these 2 cases, using these corrected eddy diffusivities resulted in an improved intensity forecast, and even for cases that underwent rapid intensification. So what's been the net result in terms of the skill of the predictions, both from a numerical modeling perspective and also just from an overall sense as far as what the observations, how they impacted the model forecasts. So what I'm showing you here are the changes in the skill of the HWRF model for 3 different versions. So a version from about 10 years ago, a version from about 5 years ago, and then a version from about 2 years ago. So this is across all lead times. So this is just a skill relative to a baseline value. So positive values indicate improved skill. And so the earlier version from about 10 years ago, you can see that there was some skill from using the HWRF model over a baseline out to about 36 hours, a little bit of skill, but then we actually had a degradation in our forecasts beyond that lead time. But now look at the version of HWRF from about 5 years ago. Now you can see an improvement in terms of the skill out to about 3 days. But you still see that drop off at 4 to 5 days. And then look at the most recent version of HWRF, or at least the one from a couple years ago. Now you can see pretty significant skill in using HWRF across all lead times. So it's really been a substantial improvement, I would say, over the past 9 to 10 years. Now this is overall, this includes a multitude of changes to the model. including resolution changes and physical parameterization improvements and so forth. But if you just try to isolate the impact of the aircraft data only, so this is using the more recent version of the HWRF model. This is a similar type of skill plot that I'm showing you now, but the black line is just showing you the change in the skill when you actually incorporate aircraft observations versus if you did not include any aircraft observations. And even in that case, you can see an improvement of between 10 to 15%, about 10% or so, let's say, depending on lead time, at least out to about 4 days or so. So it's clearly indicating that just using the aircraft observations only, we're still getting an improvement in our intensity forecasts. So now let's look at nowcasts. Through a lot of research that we've done and others in the community, one of the things that we find is that the degree to which a vortex is aligned, it's vertically stacked, gives you a sense as to what the chances are that that storm is going to intensify. So if you have a vortex with a kind of a displaced or a tilted center with height, then it's less likely to develop, at least in the near term. So here's one example from a case of Hurricane Humberto from 2019. So these are winds that are actually derived from the airborne Doppler radar at 2 different altitudes. So the left panel is showing you the winds at the 2-kilometer altitude, and the star is showing you the location of the low-level center. And then the winds at 5-kilometer altitude, you can see an X showing you the location of what I call a mid-level center. And so you can see that they're displaced. The mid-level center is displaced a little bit to the northeast of the low-level center. This information is available now in real time for the Hurricane Center, and they've actually used that information in their real-time forecast discussions. Just one example, based on this data, they said, the Hurricane Center said in their discussion, the storm is still feeling some effects of southwesterly shear and dry air, which is causing a strong tilt in the aircraft data. Conditions are expected to gradually become more conducive for strengthening. So again, this is a nice example of how the data that we're collecting is being transmitted to the ground in real time and being looked at by the specialists in terms of in helping them to make short-term intensity forecasts. This is a great example also of how they've really taken to this idea of being able to look at the Doppler radar data in real time. So this is a graphic that the Hurricane Center actually generated, and this is what the specialists can see in real time. This is showing you a swath of winds from a tropical cyclone Laura. I believe it might have been a tropical storm at this time, this year as it was approaching Cuba. So these are slices at different levels of the atmosphere, stepping up basically at every 500 meters, going from about 500 meters up to, I think, about 8 kilometers or so. And so the specialists have marked this red dot rather is the location that they flagged as the storm center. And so as you can see, as you step up through altitude for this particular swath from this pass of the aircraft through the center, you can see that that storm center again is not aligned. It's moving basically off toward the southeast. So that would suggest, at least for the short term, that the storm is not likely to intensify. However, if you look about 2.5 hours later, about 2 hours later or so, that same aircraft mission, now on the right panel, you can see that the storm center, as you step through height, it is much better aligned. There's not much of a displacement of that center as you go higher in the atmosphere. So that indicates that the storm is probably more likely to undergo intensification, in particular as it moves off the coast of Cuba back over the waters of the Gulf of Mexico. And in fact, that is what we saw with Laura. So again, this is a nice example of how the specialists are really looking at our data in real time and using that to help in their forecasts. Other types of technology, so newer technologies that we use. I showed an example of the Coyote unmanned system. So this is just a picture of how big the Coyote is. You can see it's really not that big, like a person can hold it easily. And so this is one of our scientists standing in front of the P3 aircraft. The Coyote is actually launched from the P3. So the P3 will go into the center of the storm or somewhere in the hurricane environment and release the Coyote through the dropson chute. So it's kind of like a dropson that you can pilot. And the great thing about the Coyote is that it is, of course, capable, since it's an unmanned system, it's capable of sampling conditions that any manned aircraft can really not safely go. For example, right near the surface in tropical cyclone environments. And so with that capability, something like a Coyote is really useful both for real-time monitoring of surface conditions as well as research, in particular air-sea exchange processes is another really nice application of this instrument. So this is just one example of the Coyote. It was actually released in several Coyotes actually were released in Hurricane Maria from 2017. So this is showing an image of reflectivity from the NOAA, the lower fuselage radar on the P3. So you can see the eye of the storm here in the eye wall. And so the Coyote was actually released in the eye of the storm where it says start. That white line there shows you the trajectory that the Coyote took after it was released and as it descended to the ocean surface. It actually got into the eye wall on the east side. So the right panel here now is showing you a time series basically of wind speeds from all the Coyotes that have been launched over the years. We've only had 7, I think, at this point. But again, you can see, starting from about 1.5 kilometer altitude, kind of a stair-stepped type of descent patterns, the Coyotes are measuring winds getting up to 70, even 80 meters per second as they ultimately descend down and splash into the ocean. So these are crucial measurements that we can take right at the surface to really get a sense as to what the temperature and moisture fields and the wind fields look like in that really unsafe environment. So now the final goal I want to talk about are processes. So some of the fundamental research that looks at key processes. So this is a research result that I published a few years back, where I took tail Doppler radar data from many different storms. So this is a composite type of analysis. And I looked at storms that were intensifying and looked at the Doppler data in those cases, and then storms that were remaining steady state. And I compared the structures of both the vortex as well as the convective structures and the distributions. So this is just one nice schematic showing some of the differences that we saw. So again, this is looking at things in a normalized radius framework, so normalized by the radius of maximum wind. So the dashed line here in the vertical is the RMW, the radius of maximum winds. This is a radius height plot up to 14 kilometer altitude. The shading is showing you the vorticity, or kind of the spin and the structure of the storm, both in the inner core and outside the RMW. And then the bars, the black bars, are showing you the locations of strong thunderstorms. We call them convective bursts. And so we can flag where these storms are located in a radial sense for both intensifying cases as well as steady state cases. And so for intensifying cases, you can see that the peak of the distribution of these convective bursts is located inside the radius of maximum winds. That's where the vorticity is higher. It also is a more, it's a location where the heating from the convection can more efficiently be transferred into an increase in the winds of the storm. So it's kind of a more favorable configuration for intensification. If you compare that for steady state cases, now look at the bars, you can see that the peak in that distribution is actually located outside the radius of maximum winds in a lower vorticity environment, less efficient for spin up. So that's a key difference that we've identified, statistically significant given our techniques, to distinguish intensifying versus steady state cases, just based on the radial distribution of convection. So that kind of idea has been adopted by the Hurricane Center and actually used in some of their displays. So this is a nice example, again, of ways that the Hurricane Center specialists can in real time look at some of the data that we transmit from the aircraft. This is a case of Hurricane Lane in the Central Pacific from 2018. So the shading here is showing you that the tail Doppler drive winds, I believe at 2 kilometer altitude. Actually, I think it's 0.5 kilometer, I'm sorry. So 500 meters showing you the tail Doppler drive wind speeds. So you can see the radius of maximum winds basically in this, approximately in this yellow circle. And then the white crosses here show you lightning flashes as detected by a ground-based lightning network. Of course, we can also use the geostationary lightning mapper from the GOES satellite as well to get you this information. Anyway, in this case, you can see that there's a lot of lightning flashes inside. This is at the same time, basically, that the aircraft was in the storm. You can see a lot of lightning was inside the radius of maximum winds at the time that the aircraft was in the storm. So Hurricane Lane at this point, actually, and over the next 12 hours, it intensified an additional 15 knots to reach nearly Category 5 over that 12-hour period. So again, I think this provides promise as a potential indicator of short-term intensification. So if you just take a broader brush look at the sort of research activities we've been doing at HRD with IFEX data, if you just go back and look at all of our publications over that period, and you group them into the 3 different goals, forecasts, nowcasts, and processes, you can see, perhaps not surprisingly, that the significant majority of our publications address the processes, although we do have other papers also looking at forecasts and nowcasts. And then if you further subdivide each of the topics that basically each of the papers addressed into things like TC structure and intensity change, air-sea interaction, boundary layer, precipitation, turbulence, microphysics, and so forth, you can see that most of the publications have focused on structure as well as boundary layer and precipitation processes. And really, there's been a comparative lack of focus on things like turbulence, microphysics, and the environment. So that suggests a possible gap in the research that we might want to try to address going forward. So what's the future of IFEX? Well, a key challenge, I talked about it a little bit before, is improving rapid intensification. That's really kind of the nightmare scenario for forecasters. If you have a tropical cyclone just parked right offshore, maybe 24 hours from landfall, that undergoes RI, if we don't predict that, that can lead to really catastrophic consequences. Another important goal is to improve our guidance for pre-formation disturbances. The Hurricane Center has moved to 7-day forecasts. So as a result, that requires them to basically, often they'll have to issue what we call potential tropical cyclone advisories. So if we think there's a chance of a tropical cyclone forming, they start advisories. And so we need to better understand and predict basically the genesis of these systems as well. And then really, I think we want to get beyond just to focus on intensity. We really need to focus on improving our hazard guidance in general, and that includes things like storm surge, severe weather, rainfall, extreme winds. And really that requires, I think, a greater research emphasis on microphysics and turbulence and wind structure. So just as an example for the rapid intensification, so this is an error plot similar to what I was showing you at the start of this talk. But now if you look across lead times, you look for events from 2015 to 2017. You look at, I believe these are the official forecast errors from the Hurricane Center. So if you break them down into cases that did not undergo rapid intensification versus cases that did undergo rapid intensification, so the black line is the non-RI events, and then the red line is the RI events. You can see a significantly greater error for cases that underwent RI. For example, at the 48-hour lead time, the error was basically 3 times worse than what we got for non-RI. So clearly RI is a huge forecast challenge and of huge forecast importance. So that's one reason that we're also moving toward that. And then coming back to the whole value chain idea, I think where we want to go with IFEX in the future. So, I showed this at the beginning, but really what we want to do now is we want to change or enhance our research efforts toward improving the forecast, not just of minimum pressure, TC position and peak winds, but also the wind structure as a whole, in particular the outer core wind field, microphysics, and turbulence. So that gets at some of the gaps in our research that we've had in identifying our publications. And so IFEX, again, primarily focused on aircraft data, will serve toward or be directed toward trying to improve the forecast of all 6 of those types of parameters. And then ultimately that would lead toward an improved hazard forecast, particularly with respect to storm surge and rainfall, wind gusts, and severe weather. And so, the hope is that by kind of broadening our focus of IFEX efforts, that will ultimately lead to even greater improvements in our forecast, not just in terms of the sensible weather, but also the hazards and then the downstream looking toward a value chain perspective. So I think it's a really nice way to think of how IFEX fits into this overall concept. And with that, I'll just say thank you. I'll stop presenting.
Thank you, Rob. It's impressive the assets that you have to observe these storms to start with. Yeah, and you also very nicely put it, illustrated how the observations can directly inform forecasters to improve forecasts. So not only by assimilating them, but directly feeding into the sort of the forecast process that is being done by a human being. So I have an eye on the time. So we need to cut your questions a bit short. I'd like to ask Martin to give you one question that he has selected from the chat, and then you can possibly answer other questions in the chat.
Okay.
So one question that came in from a user just called C. Can you say something about how improved information about intensity improves or changes warnings or decision making? More specifically, how long before landfall is any change in intensity information necessary to improve or change evacuation decision making?
Yeah, so one of the sort of the key time period that I've heard, at least in talking with people, for example, at the Hurricane Center, is that 72-hour period. That's kind of the time that people need to make decisions on, when to start preparing, whether it's evacuating or moving ships out to sea or so forth. So that's really, like, in terms of the storm surge modeling and the storm surge warnings, I think their focus is on about the 3-day time period that they want to be able to lock in or have a good sense as to what areas are going to be most impacted by something like a surge event. So in terms of the intensity, I think the intensity is important for surge, but it's beyond that too. Of course, it's the wind field as a whole, as well as things like the motion, the trajectory of the storm, and the geometry of the coastline. But I think 3 days is probably about what people want, at least for something like a surge event, at least.
Okay, thanks.
Mm-hmm. Yeah. Thank you very much, Rob. We take it to the other side of the Atlantic and to tropical Africa. Peter, the stage is yours. Please go ahead.